takeaways from yesterday then is that really all of these optimization problems are really extrema problems. We're finding a min or a max, which means we're finding critical values. Right? We're finding a hill or a valley where the derivative is equal to, specifically where the derivative is equal to 0. We're not even considering the non-existent case, the cusps and corners. And so that's what it boils down to. It boils down to that hard thing is coming up with that model in a single variable. So the difficult thing is probably number 2, using the constraints to express the relationship between variables so that we can do number 3, rewriting it in a single variable. Okay, that I think is the kind of the meat and potatoes. Once we get the single variable, the differentiation doesn't seem to be that bad. So 4 is where the calculus comes in. And we talked a little bit about yesterday about being able to do this without calculus as long as we just graph the function and do the max on it. And a lot of times we incorporate these type of problems in a pre-calculus class with that approach. That's kind of the entry level into calculus, sort of the access point, so to speak. Okay, so we then in the notes last night, there were 2 more examples. One was creating a rectangle under a parabola and recognizing that the width is 2x and the height was y. That was our physical model for area. And then we substituted out the y and put in the equation for the parabola to get it in one variable. And then the tricky one was the last example when it said, hey, what's the minimum distance from the origin to this sideways parabola? And the trick, I call it a trick because not many people do it this way, but the trick there is that we can just differentiate, that was a Pythagorean's theorem, and we can just differentiate the hypotenuse square. We don't have to incorporate the square root at all. If all we need to know is where, what value of x does this occur at. Because when we minimize that square, we minimize the distance as well. And so that's why mathematically it works out. And even algebraically, if you had to find that distance and you just minimize the square without the square rooting, all you have to do is square your answer anyway. So that's kind of cool. So those were the notes, and then the conclusion, what we call a good conclusion, or one that would earn both points, an answer point and an explanation or a justify point, would be to make sense of the maximum and minimum value in the applied context. So that would be including units and talking about, not just talking about x and y or something, but talking about, height and volume, or x coordinate and area under the parabola or something like that, putting it in terms of the context of the problem. So any questions about that? We're good there? Okay, and then, whoops. There we go. Okay, so today we've got some applications here, and this is tiny, too tiny to read, but this is one of the things I have in your packet is a free response, and then we have topic questions and College Board. This is obviously the free response. So just to kind of give you a preview here. Part A, you notice we have a question stem, and you know what? Right now, the details of the question stem aren't important, but we have we also have a table. Okay, that's kind of the big picture. Part A says use the data in the table to estimate the rate of change of the amount of gas. What is the only thing you can do when I give you a table? Algebra slope, exactly, right? They want we have G, gas, they want the rate, G prime. That's a slope calculation. That's the only thing. You don't have a function right now. That's all you can do. So we're going to learn something second semester that you can do with a table too. And there is literally only 2 things I could ever ask you to do with a table. One is algebra slope. The next one, part B, says that G of prime is increasing through the entire interval. and it gives you the rate, 0.2 thousand gallons per hour. Okay, justify your answer. So, so they're asking you to justify that rate. Do we know what that is an example of? When it asks you to justify a value, a characteristic? So these type of questions either justify the rate, or they're going to ask you to justify a physical value, like a G. Okay, and so you know that falls into then either a mean value or an intermediate value theorem problem. Does that make sense? Okay, remember we had those three big theorems. We have the mean value theorem, we have the intermediate value theorem, and then we have the, oh, I'm drawing a blank. Thank you, extreme value theorem, awesome. Right, those three things we have. And so this one, because it's asking you to justify a rate, this is the mean value, right? The mean value theorem, right? Mean means average. And so we're coming off of that algebra slope, which is the average rate of change. Okay. So this is going to be using your mean value theorem to say, hey, can I use this information? What does it say here? Is there a time G of T? This is a tricky one because it's saying I have this slope. Is my G of T realistic? Okay, so it's actually having you find one of the values in that slope calculation. C says I want a local linear approximation. What does that mean to you? Local, focus on the word linear, local linear approximation. Yep, so that's your tangent line. That's writing your equation for the tangent line and then using that to approximate. Does your function fall below or does your function fall above? Okay, if it's below, then your approximation is bigger, overestimate. If the function's above, then your approximation is here, littler, under approximation. So that is your, whoops, I gotta click, I guess, there you go, tangent line and concavity. Okay. And it tells you a little bit about the concavity here, I believe. There's my cursor. At the beginning there, I can't quite circle it. There we go. Okay, and then finally, the first three, we've done those. We do those problems quite regularly in every unit. Right, tangent line, mean theorem is this unit that was right at the beginning, but algebra slope and tangent line, I'm giving those problems to just about, I'm not just about, in every unit multiple times. They just show up that often. And then finally, D is your optimization problem, right? We know this because we can talk, when we read the question stem here, it's asking for an absolute maximum, okay? So we know it's an optimizing and we're trying to optimize. We want to find where the rate is a maximum. So and now we finally have a function. Again, my cursor is disappearing. I apologize for that. Where's this little arrow? Oh, arrow. There it is. Okay, so we have the function here. Okay, looks like a ratio. So it looks like maybe we might need a quotient rule there. Whoops. Oh, is it below there? Oh, that's a bummer. You can't see what's written beneath it. Let me try to, how did you know? Oh, because you're in WebEx? Wait a minute. No, I'm trying to see, I just realized something popped up, sorry, excuse me. I have something that popped up underneath here. And now, of course, I can't see. I think it just says an optimization problem, differentiate R to get R prime or something like that. Okay. Maybe I can make it a little bit smaller. Here we go. Come on. There we go. Yep, optimize to maximize. There we go. Okay. So we're going to differentiate R to get R prime. We're going to need a quotient rule there. Okay, so that's the free response you're going to work on. Our summary then, how can derivatives be used to maximize and minimize values? Derivatives allows us to find those extrema. Okay. And the extrema are the possible locations of those optimal values. You're either going to have a hill or a valley that you're going after. So we have the free response from the topic questions for day 16 in College Board. Nothing new in con. Okay, so and then we've got one more topic on Tuesday, I believe, and then review Wednesday, test Thursday. Okay, so that is up. I'm sure we can't see it, people at home, but I can fix that. We are looking on the board right up there. Too dark? Probably too dark. But we got test next week, Thursday. Probably should have the lights on. Okay, so I'm gonna let you start in on that. I'll check in with you. If you have any questions, give me a holler.
Are we supposed to work on the topic questions and the free response today?
Correct.
All right, thank you.
You bet.